employs manual laboring to to find the final quality of the product. It can be any manufacturing device, writing from mobile phones, computers, till large scale manufacturing like automobile and others, etc. So every part and every product have to go through this vigorous process, so that we are having defect free protection in our environment. And moreover, let's say this can also be applied for disease detection as well. Okay, let's say brain tumor detection, or skin disease, skin cancer, or some other disease detection is also not automated to the core. There are some challenges, I would say, but basically these are kind of manual in nature because of the severity of the content, right? So we cannot afford to lose important information to be lost, or normally like slipping through our hands. So the biggest challenge here would be the availability of data, right? Like I believe that many researchers would have taken medical domain, and their biggest challenge would be on gathering samples, and not just normal samples. It's like you need to get all the classes which are intended to. Imagine like you do a brain tumor scan, right? uh, Out of maybe 10,000 images, you'll be ending up having just 500 or 1,000 images that has brain tumor, and remaining slices or images will be nominal. We usually brain scans will be in 3D in nature, right? So it's a 3D data in nature. So basically we go slice by slice in hand, so we take slice by slice. So we might be ending up with having a lot of nominal samples, and the tumor will be present only in this area. So only like 4 to 3 slices will have tumor, and remaining will be empty. Imagine a brain scan that doesn't have a tumor at all. So we'll be ending up having lot of nominal samples, which means that more than 90 percentage, sometimes even 99 percentage of images can be of nominal samples, right? So that is a very important problem in hand. And if we see the industrial standpoint as well, on industrial area, like we could say that basically all the manufacturing process would ensure the quality is top notch, and getting a defective piece in the manufacturing process is also very minimal. Their defect ratio would be like 1% or 2% to the maximum, no matter like how complicated the process is. They have automated, and some are being even manual in nature, but moreover they try to manufacture the data or the product in a much more effective way, so that anomalies or defects are very minimal in nature. So which put us into a very big dilemmatic situation because of the data and so if we see this particular data set, it's a very popular benchmark data set. Okay, so if at all people working on this anomaly defect detection, this is one of the benchmark data set which you can always look for. This is basically MVTech's defect anomaly defect detection data set. It's a segmentation based problem. Yes, you can also adapt it to object detection based problem as well, using boundary boxes and stuffs. But the data set comprises of nominal samples like this. In the first row you can see there are many different uh, you know um, products have been manufactured, like bearing wheels, some cables, coaxial cables, and some medicine tablet cloth material, some product and some wheel, something like that, right? So these are the products which has been manufactured, and these are some defects. So you can see the defect here, right? So there's a small defect here which is available, and there's a small defect here where the additional you know what is that additional wire cuts or the bare wires are present here, and in the tablet there's a small scratch, and in the cloth there's a small hole. Likewise, you have defectiveness in every of these elements. And the zoomed up version is shown in the third row, like where you can see like how you know how these defects looks like. I would say the more challenging thing would be like this one and this one, or especially this one, because of the shiningness which you see in the material all throughout. But still we do have some defect when we zoom in close enough to to realize it's actually a defect. Now the problem is, if at all, if I ask you to create a mechanism to detect this kind of defects, the solution would end up somehow you know focusing towards every image, not just a common method which can be applied. A method can be applied only for one set of problem. Let's say I can create a method for this problem alone, but not for that method cannot be applied for the other solutions or other problems in hand, right? That's a bigger problem in hand. So respective to defects which we have in our hands, we can't simply create a generic model that can detect all these problematic images or problematic stuffs. So that's another problem in hand. But nevertheless, that's also fine. We can also derive a standalone steady fast solution for every object in hand separately, so that the efficiency can be maintained. But still, having these kind of defects are more rare, and having samples of these are also very less. I would say Imitech closely having like more than some thousands and thousands of images for nominal class, like around like 10,000 or 20,000 images, which are of nominal class. But the anomaly classes are less than hundreds. It'll be like in thousands, maybe like 1,000 or 1,500. That's all. So it's in the ratio of 5 to 100, something like that. So which means that getting an anomaly sample is very tough, and training with a normal classification or a segmentation or an object detection approach will not work. Absolutely it won't work, because of the fact we don't have the we don't have enough data to basically start with. So this is a potential problem in many industrial domains. Even many companies are actively researching many different methods that can be employed to do an automated process of quality inspection, at least a level 1 automated process of quality inspection, so that they could avoid slip through ratio as much as they can. Okay. So I guess now you found out or got the idea of how this anomaly samples look like, because if you see in these images, right, so this kind of stripes can happen anywhere. Sometimes there can be a puncture in this particular insulation area, right, and sometimes there can be some holes here, or these two would have been merged together. There can be many possible scenarios where you can get these kind of defects. Similarly, for tablet, this kind of scratch can happen anywhere, or some small cut would have happened here, some puncture would have happened here, right? Or this number 500 might have some additional contours on top of it. So the nature of defect is not very certain. Okay, it's very uncertain in nature, so that you can't go with some classic methods of identifying these kind of problems. Because if at all these kind of marks comes here in this tablet, it's very easy. You can just simply do a simple image processing method can definitely help you out in this case, right? You just do a threshold and do basic handlings, basic image processing methods, and definitely you can get this out. But the problem is this can occur anywhere in the tablet. There can be a puncture mark, there can be cut in this outer regions. It can be anything. So which means that the sporadicity of the anomaly is very high. And again, this would mean that even though I have these anomaly samples with me, imagine like I have like 10,000 of these anomaly samples, and 10,000 of these nominal samples, and I train some models. I cannot guarantee the model would be 100% accurate to detect upcoming anomalies, because it is too sporadic in nature. Even by having more images doesn't mean that it can do better. So we need to possibly cover more and more of these scenarios. The more we cover, the better it can become. That's how it has to be created. So I hope you got the idea of what is anomaly defect detection. So do we have any doubts or clarification before we go into solutions and stuffs? All right. Since there are no doubts, let's go into understanding. Yeah, as I was saying, having an anomaly sample would be very less, and negative samples or nominal samples will be very high, and that in turns create high class imbalance. So that's is a major problem which we have in hand. So you can give this a try. You can take different data sets of this kind, and train a very simple classification model or an object detection model. You would definitely see like the model will struggle hard, because we know that it's a common problem in terms of neural networks or any machine learning problems, right? So when you have an imbalance, you have to mitigate that, and in if not, overfitting would happen to the majority class, right? So since it has more instance to learn on, the weights would be fine tuned towards that direction, making it overfit towards the majority class and underfit on the minority class. So which means that our aim is to find the anomalies, not overfit towards a nominal samples. So let's see like what are the methods which you can do. One of the most intuitive and most simple method which people adopts is undersampling, and this can act as a method not only for this anomaly detection, but also can be applied for any class imbalance problems. Basically the intuitive way is either undersample it or oversample it using augmentations. But augmentations are very limited in nature. You can't just keep on creating noises and other stuffs to from 10 images to 10,000 images. That would not create better data. It might look good at numbers, but when you push it in real time as a product, it won't work. And as far in this case, what if we undersample the data? So we have the majority class of maybe 1,000 images and minority has 100 images. What if I reduce that majority class to 150 images, removing samples from 1,000, like removing like close to 850 samples and keeping 150 samples for majority class, and 100 sample which you already have for the minority class, which would definitely or maybe train a model that has a decent balance over it. But since again the data set size is very very small, so we can't expect it to be working wonders with the data. But as I was saying, yes, we can also, people have adopted different methods, especially using this image embedding approach, where the downsampling is done in a more systematic way, rather randomly eliminating images from the data. We can avoid those by using image embeddings. Okay, so image embeddings again, again, as I said, this method can not only applied for anomaly detection, but it can be very well used for many other problems like imbalance in the data set, where you have not huge imbalance, but some minor imbalances in the data set can be avoided or maintained using this undersampling method, especially using image embeddings. Now let's understand what is image embeddings in the first place. Okay, so imagine you have many data, and you have trained a model, or let's forget about the model. Let's take a pre-trained model. We have YOLO based models. We have standard classification models like VGG, Inception, ResNet. There are many varieties which we have in the market, right? So imagine those functional networks. Those network with the pre-trained weights can definitely extract features from every images that might be very relevant towards a purpose which it looks for, right? So which means that if I can use a pre-trained model, extract features and just keep it with me, not use it for some other training, or just like we use for transfer learning, we're not going to do that. We just extract features and we keep that feature in an embedding space. So that's what we call as latent space or embedding space, but usually we call it as embedding space, where it can be of multi-dimension, I would say. But basically we log the feature maps onto a space, so that if you see this particular image, similar looking images would land in the same feature space, and similar looking images will land in the same feature space, which means that every image will land it will have a feature map, and that feature vectors would be mapped in an embedding space, and definitely similarly looking images would end up closer to each other. Okay, that's the ideology of this embedding space. Now how we can employ this idea to our undersampling strategy. So what we have to do is, imagine you have, you know, some samples here, some samples here. Let's say you have, this is the 1,000 images category. Okay, so I have like 4, 5, 6, 7. Okay, maybe let's take 700 images. So I have 100 images for of every category. So instead of me blindly removing, 600 images, I can look for similar looking images. So let's say this one and this one looks very similar. So maybe I can remove any one of this image instead of randomly picking anyone, because this image looks very unique. This is also unique because of the color and maybe the texture and shape, right? So I could potentially use these guys. So vice versa, if I can able to group these things and find which is the most unique images in this particular group, based on the distance. I mean, from you can use a k-means clustering or anything. So basically, I can find the distance, using any distance calculation as well, and find the most unique samples of every class, and take like 7 or 70 images from every 100, or vice versa, 30 images from every 100 images. This way we would end up having all the unique sample, all the unique representations of the classes and the images which you have, avoiding potential duplication removal. We can avoid those duplicated images which looks very very similar against each other, right? So that is a very efficient method to remove duplicates, I would say. It's becoming a common practice nowadays, not just undersampling, but basically when you're training a model and the data set contains a lot of duplicates, especially when you create data set from from a video, it definitely, you might be having a lot of duplicate frames because of the frame rate which we have, right? So in order to avoid those kind of duplications and to avoid to get a good quality sample rather having too many distinct or too many duplicated samples, that would potentially make the model overfit towards that particular data. This would act as a better way, right? So all you have to do is just use any pre-trained model, extract the features, and push it in embedding space. So once that is done, you have the map with you. So you can select for the most common samples, most unique samples, all these stuffs can be done. And with this method, you can do this undersampling in a much more better way. And as I was saying, it's not only for anomaly detection, you can use it for other purposes as well, like basic undersampling method, or collecting important samples for the test data. Sometimes people use test data set using stratified split. That might not work out very well. What if I use is image embeddings to look for most unique samples that potentially being avoided in the test set, so that the training set loaded with all the unique and distinct samples, which helps the model learn better when it comes to push it as a product, and also avoiding penalizing the model unnecessarily by introducing a unique sample which has not been learned by the model at all. So these kind of strategies can be applied using image embeddings. And yes, this can also be applied for many other purposes, which I will say in the next slide. But this is how it looks like. You can see it, right? So you have an image. Let's say like this is from one image and this is from. So when you like calculate the distance between these two, like these two are closer and these two are closer. In the latent space, the embeddings would become very similar against it, because it's not about the pixels which we represent here. Okay, if we represent in terms of pixels, it won't work properly. But the feature extraction will look for distinct feature of this cat and this cat, right? And these dogs. So which means that like 50 or 80 percentage of the distinct features would represent cat and dog, which means that these samples will be close enough against each other. So that's the fundamental idea of image embeddings. So you extract features, you push it in a latent space, and after that you can calculate the distance between these two or these images, and you can find the closest one. So as I was saying, like this can be used for single shot image classification as well. Like what is single shot? Imagine you want to do a face recognition, right? So and the problem in face recognition, you have to take enough samples of every face so that you can recognize them anywhere you want, right? But imagine the process to acquire faces. Let's say if I'm gonna like onboard some new faces into your organization, and obviously you have to take a lot of images of the same face, right? So because in order to get better number of images, you do that. And again, the problem would be, if at all you're using a machine learning or a deep learning problem, you have to train the model again. Correct? Imagine you have 100 classes and you train the model for classifying all these 100 phases, and now there are 5 new phases which is entering. In order to detect those 5 new phases, you have to retrain the model from the scratch by adding these 5 new classes alongside with the other 100 classes. And imagine more of such classes are being added in a regular basis. Right? This would definitely be devastating for the one who is developing, right? Because he have to train this model again and again and again, so which is not a healthy way of doing things. So in order to avoid this kind of problem, you know um, people use single shot classification. They use the same embedding space method, but this time we are not going to use pre-trained methods. We'll be using a model which is trained onto this phases, of having classes. And using that particular model, we can push every images on a latent space, such that next time when you give a query image, it will go onto the space, look for the closest matching. So even though you have 1 or 2 images of every face, that's enough. You can just simply run the feature extraction on all these images, push it in the latent space, and that's all. So next time if you want to add new images, it's very simple, because we are not going to train it again aggressively for 1 or 2 days and evaluate its performance and do all these stuffs. That's not required, because now you can add images. All you are going to do is you're going to extract features and push it in a latent space. That's all. So once the feature is extracted, job done. So next time you get a query image, the new features will also act so that distance, closest distance can be identified. So this is a very essential method, which is applied in many areas, I would say, especially for one shot classification, seeing few shot learnings. It can be applied very well using this image embeddings. But again, as I told you, pre-trained model, yes, it can work for some common images which the model have seen, but it's not essential that it can work for all the data problems. So we might need to train a specific model to that particular data problem in hand, so that the feature extraction would become better in nature. Once the feature extraction becomes better and better, the latent space would look even more richer, because the way it extract features is what it's the important thing which we have to keep in mind. So which means that if the model extract better features, you get better distinguished feature maps in the latent space, so that you can get the query matched up way perfectly and easily. But if not, it's going to be a very big problem. So that's the ideology of having single shot classification using image embeddings. And yes, you can also use it for active learning, for pre and post model analysis, to see like how the model performs on similar looking images or different looking images or unique images. Those kind of analysis can be done using the same approach. So people use pre-trained models for this case, but sometimes the data is very unique. You can also use a specific model which is trained for those specific data. So this is one method. Okay, so you can use image embeddings, to downsample the data in a most effective way, so that the model can have a matched up class, data, so the model can be trained. All right. So this is one, it's not the most important or the best method, I would say, but this can lead to potential newer discoveries, I would say. As I was saying, like it's not only used for anomaly detection, you can use it for single shot classification or for many cases actually. So as a data scientist, who works in computer vision based problems, I would say image embeddings are more important, especially to analyze the data, especially in terms of pre and post model analysis. This would become hand in hand or very handy tool for us to work. Like, do we have any doubts or clarification before we jump onto the next topic? Okay. All right. So the next ideology is using k-means clustering. We all know that It's an extension of image embeddings, I would say. You have an image embeddings, you do an clustering. Imagine you have like, oops, imagine you have like 100 samples here and just 10 samples. That's fine, as long as you can have a distinct embedding space, or distinguishable information. You can cluster it with two classes. So with two classes, you might have one could be normal and anomaly, but there can be some potential problems if at all there are some more variations in this particular nominal class, and the distance between the nominal and this anomaly class is very less. The latent space distance is very very less to these two samples. K-mean clustering might not work really great. Okay, that's one more thing to be kept in mind. Or there can be one more approach where you can potentially remove this anomaly sample at all. Just remove this. Do a clustering, do a single class clustering. It clusters the entire data towards each other, right? After that, once you get a query data, you can measure the distance from this point to the central axis or central point of the image. So if this is close enough, we can say it as nominal. If it is little far away, like kind of having a threshold, but that has to be run in terms of manually. You have to run and see like which threshold value would set up the distance of nominal sample or nominally sample. That would also work, but again, as I told you, if the nominal and anomalous sample are very 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 similar against each other, only like few small portion of the images are changing. And if you see this particular image, right, I'll just look back again. If you see these images, the changes which happens in these images are very very minor. This is very minor change, and this is very minor change, and this is even more very very small minor change, right? So these kind of minor changes are potentially a big threat, because we know that it's not that easy to detect this out. So that is one thing which you have to keep in mind. Okay, so which means that yes, k-means clustering can work wonders, but if at all the feature extractions are done in a very proper way, because as I told you, image embeddings work better, but you need to make sure the domain which we are in, and if you want to have most accurate results, a pre-trained model should be a model should be trained onto these kind of images, so that you get a better pre-trained model to push it in a better latent space. If not, it will be like more of, it looks for the distinctive high level features, and it will try to adapt to that. That's the idea behind this. Okay, so yes, k-means clustering can also act as a a method if at all the distance between this anomaly and the normal are together, then definitely this would help. If not, k-means clustering might not be a better option unless and until we have you know um, a better image embeddings created for every samples, which is mostly distinguishable in nature. Then yes, k-means clustering will definitely work. We everyone know about k-means clustering, right? So if not, please do let me know. I'll just give a small gist of what is k-means clustering.
Sir, kindly say about k-means clustering, because we don't know. I don't know about it. Kindly give an
Yes.
introduction about the k-means, and then you go into it.
Yeah, I'll just go for another slide. Give me a second. I hope I have some slides for it. Okay. Okay, I'll just try to see for a good image. So, what is k-means clustering basically? Imagine you have a data like this. Okay. So, imagine you have a numerical data. Let's go with a very simpler, data in hand. So, where we have some numerical data, that's the data set, and you're just plotting in a hyperplane. Okay. Or let's take two column data. Okay. So that you have a XY axis and you plot all these data together. Now, what I'm about to do is I'm going to do a method of clustering these data into groups because I don't know the class names for it. Okay. K-means clustering is more of an unsupervised learning method. Okay. So what is unsupervised? We don't have a label for the data, but we have the data with us. Now, the only ideology is to find interesting patterns of these data, which are dissimilar against each other so that you can group those similar looking samples together. Now, what we do is, let's say, imagine if I'm going to go with three as my, number of cluster which I want to make, I'll just, try to create three markings randomly on the image and try to look for closest datas and try to form a circle like this, a circle like this and a circle like this. Okay. So it will be better if I do it in this way. Like one X can be here, another X can be here, and this can be here. So this would take, so this would take this region, and this circle would take this region, and this would take this region. Okay, because like these are the closest distance. Now what happens here is, it will try to, we just randomly, pop some, uh, data points. Since we have given clustering to be three clusters to be made, that's why we call it as k-means clustering basically. So k represents the number of clustering you want to make that you have to decide. So once you give it a number, you just randomly pop three values or two values as per the number of value which are given, and you calculate the distance. So whichever are closer, I just create a boundary. Now with these data in hand, we will again calculate the mean distance and find the central node. Let's say this is the center node for this particular cluster, and this is the recreated center node, and this is the recreated center node. So once the recreation is done, I'll again do a clustering. Now the clustering will become even more proper. Likewise, with many iterations, you can cluster things in a much more better way. Okay, so the ideology would be like, we can go with more iterations. We can stop at a point where the distance between the center node to the neighboring node are becoming minimal in nature. Okay, the lesser it goes, the better clustering it creates basically. Okay, at some point of time, the distance change from one iteration to another iteration will be very less. So that's where we will decide that, okay, so there's no much learning. It is finally done. And that is how the k-means clustering works. So basically, it's a clustering method where we don't have a label for the data, and with that information in hand, we just try to cluster and group these informations. So this is called k-means clustering. Hope this is clear. Any doubts or questions? So imagine like this particular method as numbers as a data representation. So you push it on a hyperplane and you do those sort of stuffs. But imagine if it is an image, you can do the embedding approach, which we saw in the presentation, right? So you can use image embeddings, extract features, using CNN based feature extractions. You can push all these embeddings onto a latent space, or a hyperplane, and then you can calculate the distance. And again, distance calculation, it's not a straightforward 2D distance calculation like your Euclidean distance. It'll be like multimodal distance calculations, where we can go with harmonic distance or any other different distance mechanism methods. Yes, even your Euclidean distance will work, but you have to make sure like all the nodes are being considered. So the simple idea would be like use the image embeddings, plot it onto a latent space, and then try to cluster things out using k-means clustering, or any different clustering methods, so that you can potentially circle down the nominal and the anomaly samples. So do we have any doubts or clarifications that has to be made?
Here the anomalies will be that data set will be the same as that of the normal one, or it will be a different one, sir? We are clustering it into normal and anomal. That the number of data in each set will be nearly the same or
Sorry, ma'am. Can you give me 1 second, ma'am? I'm just switching. Uh, I'm so- can you hear me now, ma'am? Can you repeat your question?
sir,
Sorry.
sir, in that K means clustering, you have made it into one is normal and another is anormal.
Yes, ma'am.
Whether the number of data inside that normal and anormal will be the same numbers or it
No,
will be
no.
different one.
It will be different, ma'am. Like how many samples we have, we will be like posting all those samples in the latent space. So let's say if we have 1,000 samples in a normal image, and just 10 sample in the anomaly, we'll be pasting in that way only. Like whatever data we have, we paste all the samples in the latent space. So this latent space, imagine like this would have 100 dots, and this will have only 10 dots. And this would work wonders if the changes in the data are very, very high. If the difference of the nominal and the anomaly samples are very different, then this strategy would work very good. If not, if the similarities are very, very high, as we see in this examples right now, there's a very minor change in the actual image. So which means that like 90% of the samples are very similar against each other. So no matter like what kind of samples or feature extraction I do, I end up having these two data points. These two circles will be very close against each other. So there's a good possibility of K-means clustering failing in this process as well. Hope this answers your question, ma'am.
Then the misclassification might be more, isn't it, sir?
Yes, ma'am. Because actually the biggest problem is we can't train a conventional classification model for this because we have a huge imbalance in the data. So it's like 10 cross 10 is to 100 or 10 is to 1,000 images. 1,000 images in nominal and just 10 images in anomaly, right? So we can't even train a model. So we are looking for alternative strategies to find these anomaly samples. So that's why we are trying with this K-means clustering, because if we have equal number of samples, then we don't even worry about K-means clustering. We can directly go with a simple classification model and be done with it. Since we have this huge imbalance, we are just trying to see like better
Go
methods
into-
to find it. Yes, ma'am.
Okay, thank you, sir. Thank you.
Yeah. Any other questions? Okay. And yeah, so this topic is little different. Okay, so it's not like a conventional day-to-day problem, but this is an active research area which many industrial people are focusing on, to create a better, anomaly detection methods that can be applied for quality inspection. So that's why, this can be little not straightforward. But yeah, if you are, finding a lag in the presentation or cannot, interpret what's happening, please do let me know, and I'll just try to, enlighten your minds. So yeah, with that, we also have one more method. Like these are the initial method which people adopted, like in 2018 and 2020, right? So that's when this anomalization became very famous of these new data set with entering into the picture. People use conventional methods like machine learning methods to do these or attack these problems. Another method which they use is one class SVM. Again, like what is SVM? I can just simply give you an overview of what is SVM. Yes, let's take this one. Let's take this one here. So imagine like very similar data with us. Instead of using K-means clustering, that's basically a unsupervised learning method. But SVM is a supervised learning method. Where again you're gonna plot the samples, but this time when you're plotting the samples on a latent space or in a hyperplane, you basically know like this is one class and this is another class. Now the ideology is to draw a margin that divides these two images as far as
possible, or these two data points as far as possible. So that's called support vector machine. So you try to create a linear boundary or a non-linear boundary that can separate, distinct different classes altogether. But this is a supervised learning method where you have the data and the label with you. So this is termed to be class A, and this is termed to be class B. That is kind of defined already before start this work. Which means that once you plot it, this data belongs to class B, this data belongs to class A. With this information, you try to draw a plane hyperplane or a line that divides these two data, and making sure the line is of the maximum distance between both the support vectors. So if you see, like, this is the edge data, this is the data which is very close to the boundary. We just make sure the distance from this line to this data and this line to this data is maximum possible, and as equal as possible for both the classes. So the better line drawn, the better result you can get. Okay. But as I told you, like, it doesn't mean that it can only be linear. It can also be non-linear in nature, which looks something like this as well sometimes. But basically, yes, this requires more tuning. Like, there are like other hyperparameter tunings like alpha and C values. Those kind of values can be changed to increase the bendability of the hyperplane or the line which you're going to draw, and the penalty reduction value as well. Okay, or increasing the penalty, making sure there is no room for errors. So you can create a hyperline like this, that supports the data. That the basic essential idea is to divide these two classes as much as we can, so that once you get a query data, let's say if I get a query data here, this evidently belongs to class red. If I have a data here and this is some data, this will definitely belong to this class yellow, something like that. Okay, so once the hyper line is drawn, you can you have the model in hand, and with the model you can classify things. But nevertheless, this is a very straightforward approach which people use for a normal machine learning problems. But how do I use this for my anomaly detection? Yes, you might be saying that, okay, I have data, like maybe I can draw a line for this data and this data. Even though this data is very less, I can try to draw a line. But the problem is, when the data is very less on one side, right? Let's say imagine you have only two dots here. Imagine I'm not having these, but I only have two dots here and here, and you have many dots. The hyperline will go here, which means that more bias will be given to the majority class. So support vector machine might not work when we keep both the classes together, especially for the anomaly detection. But instead, what if I keep only the nominal samples? What if I keep only the nominal samples and try to draw a boundary that encapsulate the entire sample process? Let's say this is the entire data sample, and I try to encapsulate the entire region using an hyperline that says that, like, whatever data is inside this particular region of interest is termed to be class 1. Whatever data which is away than this data, that can be termed as class 2. So this is also, I would say it's kind of better than compared to k-means clustering, because k-means clustering rely on clustering information, and if you don't have enough data in cluster points, you might not end up having better clusters and better distance. But support vector machines proven to be little successful, as in this case. And again, these data points can be from direct image representation, or you can use the image embeddings as well. You take the image embeddings, you plot it on latent space, and then you construct a support vector machine classifier for single class, not for multi-class. It's for a single class SVM. You encapsulate the region of interest like this, and then, like, once you encapsulate it, like, yeah, you are good to go for that. Because that's another ideology which you can work on. So hope this is clear. Any doubts, clarifications? Okay. Okay, so the methods which you saw till now is, undersampling in accordance to in like adding more information to undersampling, we can also do augmentation, which is another effective way, I would say. We can either oversample or augment the images. But again, as I told, like if the anomaly samples are very, very limited in nature and very sporadic in nature, you can't simply augment it. You have to do some, image generation methods, scans, autoencoders or something like that to create better images of anomaly samples and then use it for model training. But again, not to create GAN or some other data like that, from other models like that, requires more of this kind of anomaly samples, which means that, creating augmentations on the same images might not help because the defect can occur anywhere and you can't do that kind of augmentation just like that very easily, right? So that's a critical problem. So where you can't use the augmentation as easy like we use in other problems. But yeah, so having said, people started to use different methods. Machine learning models were not giving or were not producing enough results. It was, stuck behind like 60 or 70% of the result. So with 70% of a model accuracy, right? So it is not even a good model. You can't even deploy, those types of model, into production because we potentially know that it might miss a lot of anomaly samples. So which means that we need to have better models that can better represent the data. So the more it represents the data, like the good possibility of pushing into real time. So that's where people started to create methods that use deep convolution networks. Instead of just not using the image embeddings, but using different methods to do it. So one such method is using autoencoder. Okay, so what is autoencoder in the first place? If you see this particular block diagram, okay, so it's a segmentation based autoencoder. So the basic idea of autoencoder is to downsample the image using your CNN approach. Your very CNN approach which we use, right? Basic convolutions followed by max pooling is happening here. That's what we see in this region. This region is where your normal CNN is applied. Okay, you give an input image, and from that input image, you just try to uh, extract information and keep it with you. Okay, so let's say you extract information and you uh, keep it here. That feature extraction would be in the latent space, and from this you push it to another convolution layer, but this time we are going to have some upsampling. Instead of max pooling, we're going to upsample the data using many different methods, like just like your image resizing operation, right? So you upsample the data and create whatever which you look for. Let's say you can either do a super resolution or create mask or create a different image altogether from the input image. Anything can be done, but the expectation. Give me a second. So, it's like it can. Give me a second. So, so basically, like this. Sorry for the interruption. Yeah, that was I. Yeah. So we have this particular CNN placed, right? So we extract features. We get some latent information here, right? After this, we try to upsample this information from the latent space information. We upsample the data and we get a resultant image. The resultant image can be anything. It can be an enhanced version of this input image, or it can be a mask, it can be an object detection, it can be anything. But, so the idea is very simple. So you have an expected image that can be of anything. So the image which you generate here will try to match the expectation. So based on some loss calculation, this will back propagate, and better upsampling strategy will be provided. Not just upsampling, even the downsampling strategy will be updated in terms of weights, so that you get better representative outputs. Okay, so that's the idea of using an autoencoder. But now, how do I use this method for anomaly detection? Yes, autoencoders are basically are very successful for segmentation-based problems, but it's not necessary that you can use it for other outcomes like this, right? So you can use it for super resolution, you can use it for segmentation, you can use it for other things, but not essentially for anomaly detection. Like, how do we do that? How can we do that in the first place? But there's an interesting paper that demonstrated this process. So what they did, they used a very simple autoencoder here. The only thing is, like, this autoencoder is trained on only with the healthy images. Okay, so the autoencoder is trained on the healthy images. So the reconstruction should happen with the same image but in a different way, but showing the healthy regions of the image. Okay, let's say like this is brain scan. The similar brain scan is being generated, but the only thing is, since it is focused only onto the actual image, right, or the nominal images only, you always expect it to reconstruct with that particular baseline in hand. But imagine, like, once the model is trained in this way, and finally you are giving some brain tumor based images, that is like anomaly samples, to this particular network. Now the network will never consider this region at all. It will try to reconstruct in a better way of having it like a simple brain without that tumor. Now what you do is you use this reconstructed feature and the original image, you do a differentiation of these two. With that two differentiation, you can find what went wrong. Right? So these are the anomaly maps, which means that this is little different from the nominal sample which the model has looked for. Okay, so if you see in this architectural view, you have a very simple CNN approach. You have a down sampling and up sampling strategy here, and inside which you just take the data and you just add it, and you take the data and you just differentiate, not add it. Basically, okay, these are like, okay, this is a down sampling residual block. So they were using, okay, never mind, like, just forget about this DRB blocks. Imagine these are like some convolution layers. Okay, the main idea is to not use this kind of DRB blocks or anything. You just use an autoencoder. You apply it only onto the healthy images. Okay, the autoencoder will look for this healthy image and it reconstruct into a high resolution image or something like that. Okay, the outcome is very straightforward. You have an image, the outcome is also having an healthy image. But next time when you give an unhealthy image, it will avoid these data points because the model has not seen these kind of features. Since it doesn't know about these features, it will potentially avoid and look for a way to mask that region in a better way so that it looks like a healthy brain scan. Okay, so that's what autoencoder is. So you give any image, it tries to reconstruct into a brain that looks healthy, because that's how it has been trained on, right? So with that, once the reconstruction is done, you can just take this reconstructed output with the original input image. You just negate it. Once you negate, you get the difference of information, and you can just form a cluster onto this. Maybe like this region, is I in terms of heat map because there is a lot of differences, or the distance between the difference is too high, which potentially can be said like there is some anomalies present. So this is another method, which you can use for anomaly detection using autoencoders. It has become quite popular, nowadays. But yeah, so this is one idea of using, for finding anomalies in samples. This is like, the ideology is very simple, guys. So imagine you have a water bottle with you, right? And like how a water bottle looks like, how good it looks like. So imagine when you're purchasing it, you look for defects and tests, right? Even though we are seeing some dent for the first time, which is very different, which you have not seen in your life, but there is something wrong in that bottle, correct? Or there is something wrong in the product. Let's say if you have a small crack, small dot, a small discoloration, or different cap, different size, the fitting is not good. You have many reasons to find defective information on the product. So how do you do that? Because you know how a good sample looks like. Since you know, a template of how a good sample looks like, whenever it deviates from that particular, standard, you will definitely, term it as anomaly defect, right? That is what is happening here. So you just train at this autoencoder just to look for nominal samples alone, and it becomes very good at finding or reconstructing a nominal sample given a nominal image. But things would go crazy if you create or if you give an anomaly sample that has the defective information, and this autoencoder will not care about those additional information. It will avoid those information and it will try to mask that region with how a nominal sample looks like, which means that because of that reconstruction change which is happening, that will be the key for us to find the anomalies. So this method proven to be more successful than the k-means and the SVM, because you don't even want to use an anomaly sample at all. Anomaly sample is not even required for this case, because you just rely on the nominal sample. So more nominal sample you have, better representative latent space will be created, and once it is created, next time you get an anomaly sample, you can be done with it. Hope this is kind of clear. Any doubts or clarification? Okay. I hope things are clear, right? So these are some, recent. Yes, sir. Yes. Okay, these are good. So now let's go for the final method to do anomaly detection. So with this, we can also go for some hands-on on different areas. So the most recent, or I would say like the most advanced method than an autoencoder is using this knowledge distillation. Now, before we go into knowledge distillation, let's try to understand what is knowledge distillation in the first place and how it can be used onto a problem in hand. So basically, knowledge distillation is something like you will have two networks, potentially teacher and student. Okay. So here, the teacher network will always be better. Okay, it can be better in terms of maybe the network size can be better, or it could have been trained onto a different data set or something like that. And the ideology is to use the teacher's ability to train the student in a much more better way. So imagine you have a teacher of having 100 layers of data, or most probably like maybe like let's say 1,000 neurons in teacher network. So it's means that like more neurons and more layers potentially lead to better learning of the data, right? So the teacher would become very successful in classifying or doing detection or anything. It become very successful because it has enough capabilities to learn. But now I'm trying to achieve the same thing with just 100 neurons. Instead of having 1,000 neurons, I'm going to achieve the same performance with 100 neurons just to just to increase the simplicity of the model to avoid a lot of complexity, such that it can be deployed in real time. Because when you have more neurons, more calculation will happen, and inference time will lag, which potentially reduces the throughput, or basically the inference speed. Right? So you can push it in real time. So in order to push a model in real time, but that is as good as the bigger model in terms of accuracy, in order to not potentially sacrifice the accuracy just to increase the speed is not required here. But yes, there'd be a minimal amount of sacrifice in terms of accuracy, but compared to other methods, rather using a knowledge association, you can very well create a small model that is as accurate as teacher network. I am accurate as a bigger model. That's what knowledge distillation is all about. Okay. So all you do is you have a teacher network that has been already trained on the same data set, but with a bigger architecture size. Now you're going to have a student method. That network is going to be very, very small. like just 100 neurons or 5 layers, 100 neurons, and teacher has 5 layers and 1,000 neurons. So with this 100 neurons, now the student will try to do classification to start to learn. But before it back propagates, before it calculates its own loss, we will have an additional loss known as distillation loss. Okay, so this is a response based method where you take the logits of teacher and student and add an additional loss value towards your weight calculation. Okay, not just by having a normal cross entropy, you will have an additional distillation loss that shows like what the teacher has like classified and what the student is classified. Okay, so this additional distillation loss will train the student network in a much more confined way, or much more focused, creates a more focused direction towards it, so that the model can become good as teacher network. Okay, so that's the idea behind knowledge distillation. So that before I go to the next slide, I'm just want to know, like, is this clear? Do we have any doubts, or do you want me to rephrase this in a different way so that we can get some good clarity on this?
Sir, will you again little bit say about this?
So what we do here is, for example,
We are having to,
imagine.
one half is clear, sir, but the later on it is very difficult. We
Okay,
are having student and teacher, that is okay, but after that,
so imagine, ma'am, like now the teacher is a big network and this is a small network. Now the teacher, let's say you have a data here, data one. For this data, the logics of this teacher, let's say, because the logics are basic, not just output class, it contains all the probability of all the classes. Let's say, like, if at all we have 3 classes, it will have some logics for every class information. Now we take these logics and the output of the student logics, we use these two logics and create a distillation loss. We say like how much deviated this. Let's say teacher created a output of 0.1, 0.9, and 0.1, and the student created an output of 0.3, 0.6, sorry, 0.5, and 0.2. Now imagine, basically both the student and teacher detected the same class correctly. This is represented as class B detection, and this also printed as class B. But the only change, if I use a cross entropy, like I might be having very minimalistic loss deviations. But since I'm trying to mimic teacher, I want to make sure the distance between these two should be very, very close, and the distance between these two should be close, and the distance between these two should be close. So by using this logics information, I try to teach the student that these are the logics which I'm not expecting, because teacher is giving me 0.1, 0.9, 0.1. You should try to become more like the teacher. So next time the model perceives the same data at some point of time, this will try to closely match the logics which the teacher is bringing on. So making a double edged or a double feedback mechanism, not just by having a normal loss calculation which we usually do, but this distillation loss. Again, this distillation loss is another cross entropy method. It is also another cross entropy loss actually, but it kind of calculates between teacher and student, making the student perform very close to teacher, or how a teacher output is given. The student will also try to mimic that output, but the achievement has happened because student is a very small model. Now I'm trying to make the student model better by giving some feedback from the teacher network. That's the only thing. So if I don't have this teacher, the student will end up at 70%. Since I have this teacher network, the teacher logics will give additional information to the student of how your output should look like, and that additional loss will definitely help the student to become better. So this is the idea, ma'am. Is this clear? Like,
thank you, sir.
Yes,
Thank you.
parameters, the student mimics the teacher, right? So what are all the parameters that it will take into account?
the output logics. so like you have the output logics from teacher. So imagine like the teacher gives you a logic like your probability output or any the final output which teacher gives in, right? So we take that output and we use it for our additional loss calculation. That's all. So during the back propagation, this additional loss will be included. So the loss will look like something like this. You will have cross entropy loss plus distillation loss. So the cross entropy loss is focused towards the student network only. There is no connection between student teacher. But this distillation loss will focus towards how student is performing in terms of output of a teacher. So how closer these two guys are. So this distillation loss will guide the student to become better like the teacher. So anyways, like weight abolition is going to happen, but since this distillation loss, if it is not settling down, the weight will be updated in a more better way, so that it becomes much more closer to a teacher or much more similar looking like a teacher output.
Okay, sir. Thank you, sir.
Yeah, this is response based. Response based have limited information of a teacher output because we just focus only on the logics output which we get as a final stage. But there is also a feature based method where we do a distillation loss for every layers basically. Imagine like you have some convolution layers, right? And you do a 1x1 convolution and you select some important feature maps of every layer from a teacher, and you try to give those feature maps as a acceptable output of these layers. And now the student using the same distillation loss, it tries to mimic the feature extraction in that way as well. This is feature based. This is even more aggressive than the previous method because previous method is based on response. The outcome of the teacher is utilized. But here the intermediary outputs, the intermediary gradients of every layers of the teacher is being noted down, and the response of the student is also noted down. We try to compare these two and try to get a more aggressive distillation loss rather having distillation loss calculated only on the logics. This will be even more aggressive, making giving even more closer steps to the student, because in the previous case it just say like I want this output. The student tries to adopt it somehow and tries to give very similar output as teacher. But here it is trying to mimic every layer output should look something like this. The feature map which is being generated should be as close as the teacher's feature map. That is another method which you can also use. This is also known as the knowledge distillation, but it is feature-based knowledge distillation. Hope this is clear. Yeah, so basically like this particular knowledge distillation can be applied for many problems. Especially this knowledge distillation is applied to create a model that is smaller in nature but accurate as a bigger model, especially in terms of deployment. Knowledge distillation is highly useful. Imagine you have YOLO varieties. Like you take any object detection. Object detection has many different varieties in it, like large, small, nano, right? What if I wanted to, larger model will have more accuracy, smaller model will not have better accuracy, but it will be much faster. Imagine I have a method that can make smaller model as accurate as larger models. That would be a better thing, right? Because I can possibly push it to a edge device, and edge device can work wonders for me. So for those kind of problems, knowledge distillation works wonders. But not only that, it can be applied for many varieties of problems, especially your knowledge distillation as well. Okay, let me try to teach you that. So imagine, let us try to use this approach. Okay, now let's try to imagine ourselves using this approach for knowledge distillation. Now, what we are going to do is, now the knowledge distillation is going to be a little different here. Okay, I'll just teach you like how this will work. Give me a second. Right, okay. So imagine we have a teacher network. Okay, we have a teacher network, and this teacher network is not going to be trained at all. This is from a pre-trained model. Okay, it can be any pre-trained model. Let's say from ImageNet, BGG network or anything. Okay, you give an image, you give an input image, and this input image travels to the teacher. Now the teacher will extract some standard features, right? It will extract some standard features. Now I'm going to have a student network, okay? That's going to also extract features, and this is going to be a feature-based distillation method. So it tries to extract similar looking features as teacher. And the input image which you are going to give is only the nominal samples. Okay, it's going to be nominal samples alone. So with the nominal sample, teacher extracts some important information of that image and the student tries to mimic that. At some point of time, the student will become as close to teacher, because this time I'm not using different size architecture, because both the architecture size are the same. Teacher has 100 layers or 100 neurons. Student will also have 100 neurons, which means that student will converge to teacher at some point of time very easily. Okay, so we don't want to have a smaller model. We're gonna match the model's performance, but we are just making sure we are teaching the student from the pre-trained teacher network, so that the feature extraction looks very similar. Now that the student is trained, okay, now the student knows like what are the important features to be extracted, such that it can map the teacher. So next scenario, I'm gonna go use this method, use this model with an anomaly sample. Okay, I'm gonna use an anomaly sample. I'm going to give both to teacher and the student. Now what happens? Teacher, right? Teacher is not trained by these samples. This is a pre-trained model, right? Which means that the teacher might extract features of that anomaly samples also. So if I go to this image, it might look very easy. Imagine the teacher not only extract features of this region, it will also extract this region also. Because this looks little different and the pre-trained model looks for interesting features. And this might also be as a part of the feature set in the teacher network. But the student, which has only been trained on nominal sample, will avoid this. Very similar to your autoencoder, but autoencoder just has only one network, but we have two networks to compare with. So what happens now? Teacher will give you a feature map that will contain this anomaly sample, anomaly information also, but student will not have that. Student will not have that anomaly information. So the difference between these two feature maps will give you the result. This will be even more accurate, because in autoencoder we take the original input image and the reconstructed image to find the difference. But here we use the feature map itself to find the difference, and it can be even more accurate than the autoencoder. Got the idea, right? So is this clear, ma'am? So any doubts? So basically, I'll just repeat it one more time. What I do is I use a pre-trained model. Okay, I use a pre-trained teacher model. This is pre-trained. I give the nominal sample alone, and the teacher will teach the student like how this is how you have to extract features. Now the student trained better to extract important information on the nominal samples, because the teacher taught it so. Next time when I get an anomaly sample, teacher is a pre-trained model, so it can extract all this anomaly information also as a part of its feature, but the student is not trained in that way. The student will blindly go for this, important features of the nominal samples alone, and it will potentially avoid those anomaly features. Now the distance between these two, feature maps will increase. Based on that, you can potentially say there is an anomaly sample, and this is where the anomaly information comes. So using your, CMAP features and other methods, you can pinpoint the region of interest where the anomaly is located. So this knowledge system is proven to be much more effective than the your autoencoder approach. Is this clear? Any doubts or clarifications?
Clear, sir.
Perfect. Thanks, ma'am. Yeah, and yeah, one last thing, like this is another recently discovered paper. Now this is the state of the art method, I would say. We have also been trying to create better methods from on top of this. So what they do is it is very simpler to your knowledge discussion, but they have done it even more in a simpler way. Instead of having two networks, they use a teacher network. Okay, so they use a simple pre-trained network that will extract some features. But these are some patch features, not like normal features. These are like some, locally aware patch features, which should be taken from some, vision transformers or something like that. Okay. Those features will be used, and some core set subsampling will happen. What this core set subsampling will do, it's like very similar to your clustering method, where you, look for the important subsamples, because you might be ending up having a lot of features here, right? Because, usually bigger networks will have lot of feature maps. So you look for important feature maps. You take those information using core system sampling and you push it to a memory bank. Okay. Now testing phase, you use an anomaly sample and you extract feature, right? And you push it to this anomaly bank and you use a neighboring search, nearest neighbor. Okay. If the distance between this feature and this feature is high, then that is where the anomaly is present. And which area we have a used distance or which feature we have a used distance, that alone we will track, we can find the anomaly region. We can see that this is the anomaly segmentation match, which we easily get. So this is proven to be even more easier because what they did is like they use a patch core memory bank. Okay. So you use a patch core mechanism, very similar to your vision transformers, right? So they use a patch core mechanism to store all these, anomaly samples in a different way instead of using two networks, which is heavy, in terms of complexity and stuff. Here we just use the nominal pre-trained model. We don't even train any models. We use a pre-trained model, we extract features, we push it in the memory bank. Only this is new. With this memory bank, you just look for, it's like basically kind of a database. Okay. And you look for anomaly samples. If it is not nearby, if it's not very close to each other, you tag it as anomaly, and which subsamples are not closer, you tag those regions to find the segmentation map very easily. Okay. This is using patch core mechanism. And this has been applied onto the same MVTech dataset. If you Google this MVTech dataset, right, you can, this is how it looks like. Yeah. So this is the dataset which we are using. You can download this using this link. And maybe I'll just share this link. The team chat. Oops. Okay. Maybe I'll just push in the presentation and maybe share to the coordinator. Okay. So yeah. So this patch core mechanism is the state of the art as far as 2024 is concerned. But yeah, there is also upcoming, different methods which is recently, being created. So yeah, so do we have any doubts or clarifications?
Faculty members, any queries from your side, please raise your questions. Participants, any questions from your side?
Okay. Yeah, I'll just conclude this by showing two hands-on implementation. But since the time is of the essence, I'll just teach you like on a higher level. So like the first program which we have here is for similarity selection. So we use FAISS. It's from Facebook research team. It's like an effective way of creating a similarity search in terms of finding the real-time samples, because sometimes we might be having crore of images, and inside from millions and millions of images, we have to find the similar looking images in a much more faster way. Let's say if you're going to use it for single shot detection or to reduce subsampling the data set, this can be applied. So I'm using this transformer library. Okay, so it has been taken from this particular repository like Fires. They've used Fires method, but yeah. So I'll just share this implementation as well. It's like a straightforward method. So what we do here is we load the pre-trained model. Like this is from Vision Transformer model basically. We use a pre-trained model that will be used for feature extraction. We kind of chop the final layers so that you get features out. And with that, let's say imagine you're going to load a small data set. Okay, I'm just loading a data set that contains some flowers or say maybe leaves. Okay, so from that images, I'm going to extract features. Okay, I'm going to extract features and keep those embeddings with me. And once the embeddings are created, you know what is feature extraction, right? You push an image, the convolution neural network will go inside the CNN layers, and the feature map will be generated. Those feature map will be stored here. Okay. Once you store it, you push it in this files index. This indexing is basically a faster way of accessing all the images, because you cannot just simply go and check sample by sample to look for similar looking samples, right? Because if you do that, the complexity will be very, very high, n is to n, right? N cross n complexity, right? But this way, this files indexing is much more faster way of finding the closer sample by, even though you have a million images in hand. Okay, now that you can just load a sample image, let's say this is a sample image all I do is like I extract the feature and I just push it inside the data set with embeddings to get the nearest samples. This would basically give me the retrieved. It will give me some top 5 or top 10 samples. Or let's say in this case, top case defined to be 5. So top 5 exam samples will be retrieved and the corresponding scores will be written down. Okay. So all I do is like I extract the feature. I use the command add bias index. Once the indexing is done, all I have to do is just data set with embeddings dot get nearest samples. This will fire out the nearest sample with the scores. If you see like this for this one particular image, I got 5 similar looking images, right? So this is the query image which we are given, and these are similar looking images which I got. The one important thing which you see like this nail part is present here, right? That is also considered to be one of the features because it not just focus only on the leaf, it focus on the entire image. And if you see like all the images have focused only on the image, the remaining is blurred out. You can see similar image it's also looking blurred out. So if you see the scores, like very similar looking image will be this, and possibly this. This would be little less because maybe because of this size or different texture, you would have got this. But these 4 images are very similar looking. That's the query image. So using this method, you can use it for undersampling or finding similar looking images, which can be done very easily. Okay, so you can apply the same for your own data set. So instead of loading this data set, right? So if you instead of loading the data set, you can load your own data set, push the images, written in a TQDM format, and then push the model to extract features and be done with it. So this is one approach, and I've also used Keras tutorial to show you this knowledge distillation. So this is available inside Keras examples. I've taken it from there. So the basic idea is like I'm using Keras model. A simple CNN architecture is constructed, but I'm using a knowledge distillation to train a teacher and student as well. But this is not for anomaly detection, okay, because there's no open source code available. So we might need to develop it. There are some papers which is there, this patch core method, we have implemented a paper which you can use it. But for other methods, we have to work on our own. But yeah, this would definitely help you out to do that same outcome. So what they have done is like they have created a class known as distiller that loads both the teacher and student information, and basically it will compile these information like student loss, distillation loss, alpha, and temperature. Okay, temperature is it's been introduced in this particular knowledge distillation method. It's like very unique because they have released this paper in 2015, I believe. So they have used this temperature method to compensate the aggressiveness created during the distillation loss, because the distillation loss should not be too high because that will potentially lead the model not to learn much. It will be like unsettled at some point of time. So not to maintain that, the temperature is will kind of act as a like kind of a learning rate, to avoid the distillation loss. And alpha factor is it's like weightage given to student loss and the distillation loss. How much weightage should be given for these two bits? Okay, so because distillation loss will be like 1 minus alpha and student loss will be like direct value, something like that. So it's like opposite in nature. So, and then I just get the compile information. I get the student loss, I get the distillation loss, I get the alpha and temperature, and then I compute it. So this is how the calculation looks like. I use a distillation loss function. I'll just give the softmax prediction of teacher and the student, and then like add every loss together. That's all. Okay, this is basically what happens inside a distillation loss. Okay, a simple, I would say even you can use a simple cross entropy or use distillation loss function directly. And this is imported somewhere, right? So you can use a function to get the loss. So basically, this method is to get both the loss function and get the loss out of it. Okay. Now I just create a teacher network. Okay, I just create a teacher network here, with some convolution layers and maximum layers, and I creating a student network. If you see, like both the network layers are the same. The only thing is like the number of neurons we use is 256 and here it is 16, and here it is 512 and it is 32. So which means that like that's very less feature maps to consider, and we have too many feature maps to go with. Okay, so now I'm just preparing this. I'm just using Keras datasets method to load an MNIST dataset. and I extract, I get the training and the testing images. Basically MNIST data set, the standard data set which we use. And I'm training a teacher network now, okay, for 5 epochs. You see like the, not like the accuracy which I got is like 97. Like the maximum value which I got is 97 for training loss. Sorry, after the evaluation, we got 97% of accuracy, and this is the loss value which I got for this test data. Now I'm going to use this teacher's learning information or the logic information to the student by using the distiller class which we just created. We give the student and teacher models inside it, and we just compare it. Once this comparison is done, I use the model to train for 3 epochs, not even more, just 3 epochs. And you see the loss, so the accuracy of the student becomes 97, and here it is 97.6. Very, very small difference, okay, in terms of number. And just to show you the comparison, if I just train the student from the scratch, the result which I got is 97.6. Okay, so it's like, okay, did I miss something? Yeah, so like, it's like just train for small number of epochs, right? But once you train it for larger epochs, the student network will become evidently better compared to the student trained from scratch. And again, this data sample is very simple, right? The MNIST, you know about MNIST, right? So MNIST works very easily for any architecture. Even you use a neural network, it works. It gives you 99%. But this is the idea. Okay, so once you hope you got the idea, right? So use the distiller method. You push both the models together, and you just train it with additional, distillation loss as an category for the model to evolve. In this way, you can use your knowledge distillation to train any model. So this can be applied for object detection, segmentation, and even for anomaly detection. Only few minor tweaks can be done. Accordingly, you can make it work. I'll share these two notebooks to the in chat so that you can also look onto this. So do we have any doubts or clarifications?
Sir, how we can select the number of neuron layers for the particular teaching and student training purpose?
We can choose the number of layers as we want. So let's say in this case, I've chosen to go with 2 convolution layers and 1 max pooling. We can increase or decrease as per our requirements. And the neurons can also be maintained. Like this is having 256 neurons, 256 convolution feature maps or convolution filters, and this is having just 16 filters.
Yes, sir. Sir, it depends upon the number of features we can select the neurons. Is it correct, or how we can select the number of neurons for the particular problem?
Yeah. So basic thumb rule would be like the data set is very complex. We can go with more and more layers and more neurons. If the data is not that complex, we can potentially go with a smaller sized network as well. More the complexity, more the neurons. That's how it is. But we cannot do it vice versa because it will potentially overfit. Yes, sir. Sorry.
It depends upon the trial and error method. We can need to select the number of layers. Is it correct, sir?
Yes, sir. So we can go. We can just analyze the data sets before we train the model. We can see like how complex it is. Based on that, we can judge like this method would work, and maybe fine tune like 3 to 4 trial and errors can be applied to to find the right optimal layers. Okay. Yes, sir.
Thank
Any
you.
other? Thank you, sir.
Yes, sir.
Any other questions?
Any other questions from participant side?
Deepanraj
sir, thank you, sir.
Yes, ma'am. Thank you, ma'am.
Ma'am, go ahead. Go ahead.
Yes,
is there any thumb rule that for each and every future 1 neuron can be there like that? Is there any thumb rule, sir? If the number of features is 10, then 10 neuron has to be there, like that.
It's like we won't be having neurons in a convolution layer. Like we certainly, you know, consider it as a filter. It has multiple values inside it. For every value, will act as a weight, basically. And okay, maybe for dense layer, yes, like again, like dense layer is basically mixing all these feature maps together, right? So like more the dense neurons, more mix of information from these feature maps should be represented, but not necessarily like this should potentially create more complex nature of the data such that it might overfit to the current problem, because sometimes the data might become very simple for this architecture and it will exploit the data and look for noises at some point of time. So we should potentially avoid that by having an optimal value, which can be analyzed further with the graphs, like see like whether the model overfits quite quickly for the current data set. So based on that, we can optimally like measure it. So there are no certain thumb rules, but yeah, one advice would be like if the data set is quite large enough, if we have decent number of samples, like more than 20,000 or 30,000 samples, we can go for standard ImageNet or COCO based data sets, COCO based models. There are some standard models like VGZ, Inception, Testnet for classification, YOLO models for object detections. We can use those standard architectures to start with. And if the results are fruitful, we can stick with that, or we can just make some minor modifications. But if we have data set that is lesser in size, the size of it is very less, then we have to go with some conventional methods like having some few convolution layers. This should become more of a trial and error method now at some point of time.
Thank you. Thank you. Thank you very much.
Thank you, yes.
Thank you, sir. That was a very informative session. Thank you very much, sir.
Thank you. Thank you so much for the wonderful opportunity, ma'am. Thank you,
sir. Thank you, sir.